So that PDF you sent, right, sir? I also took Xerox, sir. That
Which one, beta?
PDF of question answers.
Which one?
Uh, sir, you sent. Sir, you sent the Telugu Academy
No need, you
basic
can read it from that one only.
material.
I'll tell you at that time. Don't worry. First try to complete this weekend syllabus.
Okay, sir.
Then I'll tell you what to do with that. Okay?
Okay, sir.
Sure. Has that one another boy also joined it, beta?
Yes, sir. He has to join, sir. I'm not going to join from you.
He's still able, not yet joined.
Yes, sir. Sir, which college is he in, sir?
Page.
Page, yes.
Sure. Okay. We'll start with thermodynamics, beta, no? Okay.
Yes, sir.
Sure. Let us try to discuss the first part in this one. State and explain first law of thermodynamics. First law of thermodynamics. I hope you remember the first law of thermodynamics, beta. Can you refine me once?
Yes, sir.
First law of thermodynamics is also called as what? Float. FLOT. First law of your thermodynamics. Isn't it?
Yes.
How do you define this one, beta?
Yes, sir.
The amount of heat supplied to any system is equal to what? Sum of the change in internal energy of the system and also the amount of work done by the system. Like say for example, if I
Yes,
give
sir.
you 100
DQ is
rupees or
equal
maybe
to.
like say for example 10,000 rupees. So what happens first? You feel happy
Yes, sir.
seeing that 10,000 rupees. That means internal energy of the system has been increased. And with that 10,000 rupees, you can do certain amount of work. That means you can buy your clothes, you can buy a game, or you may be buying some kit, anything depending upon your requirement part affiliation, isn't it? So whenever I give certain amount of your
Yes,
energy
sir.
in the form of your money, that will be increasing your first your happiness. The next one is you can use that money to buy something else, isn't it? The same thing is happening here in the also
Yes,
first
sir.
law of thermodynamics. So I can write that it states that the amount of heat supplied, the amount of your
Yes, sir.
heat supplied to a system is is equal to the is equal to what? The sum of the change, the sum of the
Change in
change in internal energy. Sum of the change in the
work done.
internal energy of the system, of your system, and and the amount of work done, and the amount of external work done, by your system, external work done by the system particulation. So what I said, amount of heat supplied to your system is equal to what? It is equal to your sum of your change in your internal energy of the system and also the amount of your external work done by your system, external work done by your system particulation. Is that clear?
Yes, sir.
Like say for example, if I'm giving you the small amount of your heat in the form of dq, then that part of a dq is being used to increase what? Internal energy, and the remaining part of energy is being used in doing what? External work done. So I can write here mathematically
Work.
dq will be equal to how much beta? Dq will be equal to your du plus of your
du plus dw.
dq is equals
Yes.
to du plus of your dw part affiliation. So if I'm writing the sign convention for this one, this is very important even for your competitive examination and also your board examination. The first thing is right now you see work done will be positive if work is done by the system. dw is positive. dw is positive if the work is done
By the system.
by the system. If the work is done by the system. Number two, work done will be negative. Work done
Work is
is
done on the system.
if the work is done on the system. If the work is done, if the work is done on the system. Work is done on the system. Okay. And third one is dq. If I'm writing the value dq, that means energy whatever you're supplying. dq is equals to positive if heat is supplied to the system. If heat is supplied, to system. Okay. And in the same way, dq will be negative. When it will be negative, beta? If it is taken out from the system.
From the system.
Yeah.
Yes.
If it is taken, out from the system. If it is taken out from the system. Next one is internal energy. Internal energy is positive if we increase the internal energy and negative if we decrease the internal energy, because it is a function of what beta?
Yes.
Temperature. So I can write here right now du is equals to positive for increase in internal energy.
Sir, actually this question came, sir, in the examination also.
Okay. du is positive for increase in your what? Internal energy. And the same way du is equals to negative for what? Decrease in internal
Decrease.
energy. Decrease
Yes.
in your internal energy. Decrease in your internal energy. Okay, so this is the thing you need to write whenever is asking for a 4-mark question. What is, you explain the law of conservation? What do you mean? First law of thermodynamics or first law of thermodynamics? You need to write the first law, then explain dq is equals to du plus dw, then write your sign conventions part affiliation. Then we are also having certain limitations for this one. Limitations. The first one is this law doesn't explain you the direction of heat flow beta. In which direction is the flow of your heat? This law doesn't give any explanation because we're just telling that dq is equals to du plus of your dw part affiliation. So I can say that
Yes.
this law does not explain the direction of heat flow. Does not explain the direction of your heat flow. Okay. And it also doesn't tell any efficiency
Yes.
with which heat is been converting into the work part affiliation. So I can write that
Yes, sir. The relation between.
it does not tell about efficiency. It does not tell about your efficiency with which heat can be converted into work. It can be converted into your work part affiliation. That is a basic limit which you need to remember in this one beta. Yes, beta.
Yes, sir. Nothing, sir.
Okay.
Yes.
So that was about your thermodynamics first law. So first law of thermodynamics says that the amount of the heat supplied to your system is equal to what? Sum of the change in internal energy of the system and the amount of external work done by the system. So dq will be equal to du plus dw, and sign convention. dw is positive, work is done by the system, and it is negative if the work is done on the system. dq is positive, is applied to the system and dq is negative, heat is given out from the system. The same way internal energy is positive if there is an increase in internal energy, and if there is a decrease in internal energy, that will be equal to negative. What is the limitation of this one? The
Yes.
limitation of this one is it does not explain about your direction of your heat flow and does not tell about your what efficiency in which the heat
Efficiency.
is converted into your work participation. Done?
Yes.
Sure.
Yes.
Next one, again, very important derivation beta. See this. Relation between your two specific heats. A relation between two specific heat capacities. Specific heat capacities of your gas. Based on the law of conservation of your, based upon your first law of your thermodynamics. Based upon your first law
Yes.
of your thermodynamics by definition. So we are talking about right now the relation between your two specific heats of your gases on the basis of your first law of your thermodynamics. It is a little bit of complex, but it's really worthy to remember better. So make sure that you try to remember the basic condition. See, for example, for this one, what you do is, first we'll try to draw a container. I'll take a shape. Yeah, I'll take this shape right now here. Yeah. Okay, this is a cylinder.
Yes.
And to this cylinder, we are attaching a piston somewhere here. Okay. So this is the piston beta, in which certain amount of gas is being filled first. This is the amount of the gas which is being filled. Okay, and this is
Yes.
your piston right now. What we are doing is right now, see, we are considering 1 mole of an ideal gas is being contained in a cylinder provided with a frictionless piston. So right now, I'll write the statement here right now. Consider 1 mole of an ideal gas. 1 mole of an ideal gas contained in a cylinder provided with what beta? Provided with a frictionless piston.
Frictionless piston.
Provided with your frictionless piston. Now, area of cross section of the piston is, say for example, A. Pressure and volumes are being given in this one, are the temperatures and pressure. Now see, when I increase the temperature of this gas beta, isn't it? So now the pressure of this one is P, volume is V, and temperature is, say for example, of 80. So the moment I heat it right now, what happens? The gas will get expanded. So I can write here 1 point.
Yes, sir. Piston moves up.
When the gas inside the cylinder, is heated, the piston moves in which direction beta? The piston moves up by a distance, say for example x. Small distance I'm going to say for example dx. So I'm already drawing here right now. This piston is, say for example, has come here right now like this. Okay, it has been moved a distance of here, how much for me? Dx. Okay, na?
Yes.
something like this. It has been moved by a distance of your dx part of relation.
Yes, sir.
Okay, now if I am writing in these two cases,
Yes, sir.
now see here, case number 1.
Sir, is there too much volume coming from my side?
Is better?
అంటే నా దగ్గర నుంచి ఎక్కువ వాల్యూమ్ వస్తుందా సార్?
No,
Should I
no,
decrease?
nothing. It's not. It's perfectly okay. Okay. Now
Okay,
case
sir.
number 1.
Yes.
Case number 1. Heating of gas. Heating of gas at constant volume. At constant volume. So if I am heating of your gas by keeping what better? Volume constant. By keeping
Volume constant.
volume constant. So when gas is heated at a constant volume, heat supplied is given by how much better? dq is equals to your n into cv into dt. So I can write here right now.
Yes, sir.
When the gas is heated, at constant volume, at your constant volume, the heat supplied is given as, can you tell me how do we do it this one? D cube is equals to your n into cv into your dt. N value is how much for me? 1 into this one is cv into your dt. So that will become for me cv into your dt. So this is the value of your
Yes.
d cube. So okay. So this is the value of your d cube. D cube is equals to how much I'm getting? D cube is equals to your cv into your dt. Okay. Then from first law of thermodynamics,
And volume is
yeah, from first law of thermodynamics, I know the relation dq1 will be equal to du plus of your dw, isn't it? So I can write here du is
yes,
equals to how much for me? Du is equals to du plus work done will be equal to 0 because at constant volume, because at your constant volume work done will become for me how much?
volume
0 because dw is
0.
equals to p into dv. So volume is constant means differentiation of this one will become for me 0. So I can write here right now dq1 will be equal to your du, isn't it?
Yes, sir.
Isn't it? So I can write here dq1 will be equal to your du and that value will be equal to how much better here? Cv into your dt. That will be equal to your Cv into your dt part of relation. That means internal energy value, I'm getting this one as this. So this is my equation number 1.
Yes.
Then the next one, case number 2. Case number 2. Now what I am doing is heating of your gas at constant pressure. Heating of your gas at what? At your constant
Constant
pressure.
pressure.
So now I am heating the gas at your constant pressure. Okay. So when I'm heating the gas at constant pressure, heat supplied is given by how much beta? Heat supplied is given as dq2 is equals to number of moles is 1 into this one is cp into your dt. That means this will become for me cp into your dt. Can I write like that?
Yes, sir.
Now
Yes,
from
sir.
first law of thermodynamics, we know that dq2 will be equal to your du plus of your dw, isn't it? So dq will be equal to how much?
Yes.
dq2 is how much right now I'm getting? Cp into your dt. Du will be equal to how much beta? Cv into dt. See, already I got right now above value from equation 1. I can substitute the value of
Yes, sir.
du. Du will be equal to how much for me? Cv into your dt.
DT will get
Yeah,
cancelled.
this will be your work done dw, isn't it?
Okay.
Now this is the way which I can write Cp into dt is equals to Cv into dt plus of your work done. Now work done on the gas is how much beta? Work done by the gas. Work done by the gas on the piston is given as, Can you tell me how do we can write? Work done is equals to force into your displacement. Force will be what? Pressure into
Yes.
area into your d into your x. And you know that area into dx can be written as of your what? P into your dv. So dw is equals to how much for me? Your p into your dv I can write. This is my equation number 3. And cp is equals to this one. This I'm taking it as of your equation number 2. Okay. So what is P here, beta? Atmospheric pressure outside the piston. So from equation 2 and 3, what I can write? See, from equations 2 and 3. 2 and 3. What I can write? Can you tell me? From equation 2
So
and
we
as
can
well as of your
substitute
3.
the dw.
Yeah. So Cp into your dt I can write here. Cp into your dt is equals to your Cv into your dt plus of your work done will be equal to your pressure into your change in volume. So all the Cp terms you can take on one side, beta. So this will become for me Cp minus of your Cv into your dt is equals to your P into your dv. Can I write like this?
Yes, sir.
Now see, from ideal gas equation, we know the relation PV is equals to how much, beta? PV is equals to NR into your dt. N is how much here? 1. So I can write here PV will be equal to R into your dt. Can I write the P into dV is equals to R into dt? So I can write here P into your dV will be equal to your R into your dt. Can I write like that? So actually, I need to write like this, something like this. So if I write like this, you'll get a clarity. So I'll write this one first, like this and this one. See here, we know PV is equals to N into R into your T. When I'm writing for a small change, I'll be writing this one as P into dV. N is 1. So this will become for me R into your dt. So that is the reason P into dV is equals how much for me? R into your dt. Isn't it? So this is my equation number, say for example, Cp minus Cv. This is my equation number 4. This is my equation number 5. So from 4 and 5, what I can write here, see? From 4 and 5, what I can write you see? Cp minus Cv into your dt is equals to your R into your dt, isn't it? So dt gets cancelled.
Sir, your voice is breaking, sir. I'll just rejoin, sir.
Voice is breaking, huh?
Yes, sir. I just rejoined, sir.
Might be signal problem.
Yes, sir. I just rejoined, sir.
Now? Okay, now Cp minus Cv, what I can write better? Cp minus Cv is equals to your R. So this relation is also called as a what? Mayer's equation or Mayer's relation. Okay. Is it fine, beta?
Yes, sir.
Okay, na? Is it audible, beta? No.
Audible.
So that was about your Mayer's equation or the relation between the specific heats of your gases. So what we are doing, we are considering 1 mole of an ideal gas contained in a cylinder provided with a frictionless piston. When the gas is inside is been heated, the piston moves up by a distance of dx. First case I'm taking heating of the gas at constant volume. So when the gas is heated at a constant volume, the heat supplied is given by dq is equal to N into Cv into dt. N value is 1, Cv into dt. So dq value is how much for me? Cv dt. From first law of thermodynamics, from the first law of the thermodynamics part of relation, dq will be equal to how much for me, beta? Du plus of your dw. So dw is 0. So I'm getting right now dq is equal to how much for me over du plus du. That value will be equal to your Cv into your dt. Next one is heating of a gas at a constant pressure. Heat supplied at a given gas. So dq will be equal to how much for me? N is 1 Cp into your dt. So Cp into dt is your dq2 value. From first law of thermodynamics, again I'm getting right now from this one, dq2 is equal to du plus dw. So dq2 value is how much for me? Cp into dt. Du value is Cv into dt plus dw. So work done by the gas on the piston is given by how much? dw is equals to your F into dt. So from that one, I'm getting the formula dw is equals to your P into dv. So from equation 2 and 3, I can write Cp into dt is equals to Cv into dt plus P into dv. You take all the dt terms on one side. So I'm getting Cp minus Cv into dt is equals to your P into your dv. So from ideal gas equation, we know PV is equal
Yes.
to nRT. So P into dV is equals to your N value. I'm taking 1, R as it is, dt is nothing but T. So PV is equals to how much? P into dV will be equal to your R into dt. It is equation number 5. So from 4 and 5, I can simplify the relation, substituting the value of 5 in equation number 4. So Cp minus Ev is equals to your R. We are getting the relation. Cp minus Ev is equals to R, which is also called as of your Mayer's relation. Is it clear?
Yes, sir.
Any doubt?
Sir, once can you show the bottom once, like the ending after PdV is equal to RD?
This one?
Yes, sir. One more. Okay, sir. Got it, sir.
Okay. So just try to do these two questions once again and try to write it once or twice, and without seeing you
Okay,
try
sir.
to write this question, that will be helpful. How much time is left out, beta?
Sir, warning didn't come, sir.
Is beta?
No warning came, sir. Nothing came.
No warning has coming. Yeah? Okay, chalo. ఈ రోజుకైతే ఆ రెండు చేసుకున్నానా?
Okay, sir.
Okay. Then remaining part we'll try to do it in the tomorrow session of the class. Okay. ఈ రెండు ఒకసారి చూసుకొని
Yes, sir.
వితౌట్ చేయడం రాయి, దాని తర్వాత ఇంకా 2 డెరివేషన్స్ ఉన్నాయి, that will take time, so that will try to do it again tomorrow. Okay.
Okay.
Okay. Take care. Bye. Bye.